All right, hello everybody. Welcome to EEE 135. This is Chapter 7, Wind Power. So first thing we should talk about is kind of the physics of what wind is. We talked a little bit about it in Chapter 1, but we're going to go more detail here. If you recall, wind power comes from the concept of air pressure variations. So you have high pressure with a bunch of air molecules packed tightly. You got a low pressure area with not that many molecules. So the molecules always want to disperse evenly around. So the high pressure molecules will move to the low pressure molecule, and the molecules physically moving is the wind effect. Okay, so as wind blows on you, it's literally invisible molecules pelting you and pushing you back. That's how you feel the wind. Okay. Now, pressure can be described as force over an area. So you think of a specific area and there's a force pushing in on it. That's how much pressure there is. Okay? High pressure means you're getting squished. Low pressure is kind of wavy and open air. Okay. Force is always in newtons and area is meters squared. Okay. Now, there are many different units to describe pressure. The official SI unit is called a Pascal, which is 1 Newton over 1 meter squared. More commonly, you'll see other ones. One is a millibar, which is equal to 100 pascals, because the pascal that's a very weak unit, right? In America, we will typically use PSI, pounds per square inch, and this is about 6,895 pascals. Another one you might see is millimeters of mercury. This is a barometric pressure. So you might see like a little glass tube with mercury in it, and how much ever it moves around, that's a pressure difference. Okay. Another one is atmospheric. So ATM stands for 1 atmosphere, which is the pressure exerted at sea level. So think about if you're standing on the ocean, the amount of pressure you're feeling, that's like 1.0 or 100%. So atmosphere is a normalized number to sea level. Okay, so if you go higher up to the mountains, you're going to get like 0.9 atmosphere. If you pressurize it, like in a building, you might get above 1.1, 1.2. Okay. So that's an ATM is another unit. Okay. Now convert an ATM. ATM is 760 millimeters per mercury, or 14.7 psi, or 101 kilopascals. 14.7 psi is probably a more common number. Some probably heard it somewhere in your lifetime. That is the pressure at sea level, or 1 atmosphere. Okay, so you're probably burning your brain. 14.7 psi is a sea level pressure. Okay. So if you ever need to look at some instrumentation, that's what you'll typically see. Okay. Now, talking about wind direction, excuse me, wind always blows from high pressure to low pressure. We've talked about that plenty of times. But there are different layers of wind. You might have something called boundary layer wind, which is the lowest part of your wind front. It's typically what you feel on the ground, and it's the wind that skirts the Earth's crust, right? Now, this wind, it's because it's on the Earth, it's going to bump into many things, right? If you have a little hill, you have a tree, you have some buildings, it's going to kind of bump and move around it, block it, right? So the boundary layer wind is very turbulent, very unpredictable speed, because naturally things will block it. Okay. Now, if you can move higher up past the trees, the hills, and the buildings, you'll have a clear sky that's unimpeded. That's called a gradient wind. Okay. That's the middle part of the wind layer. It's higher than any obstacles on the ground because nothing's stopping it. It's going to be a smooth, constant wind speed. So if you imagine how we build wind turbines, at the bottom base, this is where you're going to have your boundary layer. Even the wind turbine's tower itself is splitting the air around it, and that's where you get your turbulence. The higher up you go to where the actual blades are, that is this is probably like 50 meters high or 150, 160 feet high, right? That's like 10 stories. That's probably your gradient wind where it's nice and smooth because there's nothing obstructing it. Okay. Which wind is best for wind turbines to harvest? Yeah, obviously the gradient wind because it's constant wind speed, right? We don't want wind to turn on and off, change directions constantly. It's going to be a hassle to harness the energy efficiently from that. So we just want nice, smooth wind flow. That's why we build our wind turbines very high up, okay, unobstructed by other obstacles. Okay, so gradient wind good, that's where we want to target. We talked about coastal wind patterns, get a little more detail this time. So there's two types. The first one is the sea breeze. This is a more common one. You see this a lot in California coastline, especially as you go north, right? And the idea is in the daytime, so the sun rises, we're like 11 a.m. The land is always going to warm up faster than water. It's always been like that. Water holds on to temperature better than land will. Okay, that's why you ever live near a body of water, your temperature will be more average than maybe somewhere in the middle of nowhere. This is kind of why Sacramento heats up and down all the time, but then the coastline in San Francisco stays at a more constant temperatures because the water nearby helps level everything off. Okay, so land will always get warmer faster and before the sea will. So let's say 11 o'clock. The land is hot, the sea is cold. Now, the cool water will then make the air cool as well. And the land will have hot air on it. So what happens to hot air? It rises. So in the daytime, the sun heats up the land faster than a water body. Warm air will literally rise up into the sky, right? Because the air is leaving, you're creating a low pressure system on the land. Okay? And in a cold sea air, cold air packs up and is higher density, it'll then want to move onto the land. So as a warm air goes up to the sky, the cool air on the sea will sweep in to take its place. And that's where you get that cool sea breeze. And this is pretty constant. Every day as the sun rises, cold air is going to always come in and take its place. Okay? Now, conversely, the opposite side, some places, it's kind of much more rare, but you can have something called a land breeze. This is kind of opposite effect in the nighttime. The sun is gone and the land will cool down quicker because the land can't regulate its temperature as good as the water can. So maybe let's say 2, 3 in the morning, the land is going to be cold, but the sea might be warm still. So you can get an opposite effect where the sea will have warm air and the air will lift into the sky. And then the air on the land, which is cooler, is going to come it'll flow out into the ocean to replace the warm air. Okay? So basically, a land breeze is when the wind flows out into the ocean. Okay, so this is all just based on air moving up and down and replacing it and pressure differential. Okay. Now again, land breezes are much more rare and they're also weaker. So typically the sea breeze is the more dominant one. Like in California, we always get sea breezes. Very rarely do we get land breezes. Okay. So that's another part we need to think about when we do wind turbine design. Another factor that we cause from the wind turbine is turbulent airflow. Now, if nothing's in the way, the molecules in the air will go in straight lines as the wind blows, and it's not going to move much unless it hits an obstacle. Okay, that's called laminar flow. This is air molecules that move in a uniform straight pattern, unobstructed. And the nice thing is there's whenever wind will blow this way, there's equal amount of force in all area the wind blows. We like equal amount of force because then when it hits something, there's equal distribution, there's less mechanical stress. So we want nice, smooth wind to hit the wind turbine. Now, unfortunately, the wind turbine itself is going to chop up the wind. Just the blades moving is going to split the wind. So if you ever stand behind a wind turbine, the air is going to go all over the place. It's going to be swish swashing all over the place. It's going to be very loud, very you can get battered by the wind. It's going to be a bad time. Okay. This is very turbulent airflow. Turbulent flow is when the air molecules move in a wavy, non-uniform, and unpredictable pattern. Okay. And you can see the wind, you have smooth laminar wind hit the wind turbine. The wind turbine is going to chop it all up. So everything behind it is going to be very turbulent. We call it a turbulence zone because all the air molecules are just swishing all over the place, and they need time to settle back into a smooth pattern again. It will eventually, but just it takes time. Okay. And it might take like 100 meters of distance before the wind smooths out again. Okay. So what does turbulent airflow cost for wind turbines? Right? If you ever flew in an airplane or heard seen in movies, when they hit turbulence, it starts shaking all over the place. The exact same things that happen to wind turbine. Certain wind direction, speed, and vibration shifts because this unpredictable flow will cause loss of power, mechanical stress. It can start vibrating a lot. And that's bad because you'll prematurely break the wind turbine at worst, and even quote at best, you're still losing a lot of power, which is just money lost. Okay. So in general, we like laminar flow. We don't like turbulent flow. Okay. So we're going to design and choose our site to make sure we get as much laminar flow as possible. Okay. Now, once we start talking about wind turbines, we need to start looking at different models out on the market. Every wind turbine will have something called a wind power curve. Depending on the way the turbine's built, the material used, the number of blades, the size, everything in the construction will have a unique maximum output. So every wind turbine is mechanically designed to operate at what we call a rated wind speed. There's going to be like a small window of wind speed that this is perfectly designed for. And if you try to go outside that, you can get suboptimal results. So in this case, on the left-hand side, you can see power output. Obviously, we want more power. More power equals more money. So I want the highest kilowatt possible is going to be up to 60 or 70. The way the wind turbine was designed mechanically, at low speed, it doesn't even turn. And it barely picks up. It only gets until it gets somewhere between 14 to 18 meters per second, the wind velocity. That's where we get our peak power. So I would say what would be ideal wind speeds for this particular turbine design? We want to make sure this is installed in an area which has wind speeds between 14 to 18 meters per second. Okay. Otherwise, pick another design. Okay. So if I have this place with only 10 meters per second wind, don't buy this wind turbine. You're wasting money. Go buy another one that's suited for 10. Okay. This is kind of they typically, if you're lucky, the manufacturer might give you a chart to show you the exact wind output per speed difference. So you can see to kind of graph it out, you got 2, 3, 4, 5, 6, 7, all the way down to 21 meters per second. That's the wind speed and meters per second. You got wind speed in miles per hour if that helps, because if you don't know what 10 meters per second means in your mind, that's about 22 miles per hour. Okay, 17 is about 38 miles per hour. Okay, so don't get me wrong, 40 miles per hour wind is pretty strong. Okay, now look at the power. If you see the numbers go up, where does it peak out? It peaks out right here. It goes from 63.8, 64.7, and then it starts going down. So 17 meters per second or 38 miles per hour is the exact peak power. But I would say anywhere, what we said, between 14 to 18, maybe 15 to 19 will be good. Somewhere around this range, we're okay. Look at 10. 10 is 41. That's, 60% of what we should be getting. That's not good. Okay. So how did they get these numbers? How did they make this graph? Did they just pull out the butts? No. They do testing. So once you get a good wind design, there needs to be some way to prove that this works as intended. Right now, I can make a company and say whatever I want, but you have to trust me. If you don't know me, how do you know that my stuff is good? Right? This is where standards come in. Standards is a kind of the unique or internet, some are international, some are American only groups of scientists and engineers who will test equipment for you. And if they pass, then they get the standard, the stamp of approval. Okay. So buying a wind turbine, you want to make sure it's certified by National Renewable Energy Labs. Okay, so these are national, this is a government agency. It conducts standardized testing on all wind turbines and generators. So when you try to buy something on Amazon, am I buying a piece of junk or not? You could go to the NREL website and say, hey, did they reference this? Is there material to prove that this is a good wind turbine or is it a piece of junk? Okay. Now, how does the national lab do this? Well, they have to scientifically derive the most efficient wind turbine designs. That's one of their jobs. Okay, that's the whole reason why we do this test is to say design A is the best, B and C and D are not as good, right? And as a consumer, you need to know which one's the best or which one's the worst, so you're not getting cheated. Okay. Now, what's one of the examples that test they use? They use a wind tunnel test. So that inside the building, they have a bunch of fans that will artificially create 40 miles per hour winds to blow into the wind turbine, and we can observe what's the power output, right? We could observe is the vibration, right? The temperature, everything is because it's in a closed environment. We could fully control which direction the wind's coming from, the speed, the air density, everything. It's like a perfect experimental laboratory. Okay, so wind tunnel testing is used to observe the performance at various wind pressure and speed levels. And it's kind of also example, they could put a little canister of gas on the wind blade tips, and you can see as it spins, it creates a little smoke effect, and you can see kind of the trail of smoke and can see is there any vibrations, how fast is it, what's the gap between the smokes. It will tell you a lot of information to then ultimately judge the performance of this wind turbine. Okay, so standardized testing is very, very important, mainly for the consumers, so you're not buying junk and wasting your time. Okay. All right. So let's do a couple. Let's get a little bit into the math and the calculations. So this, and we're borrowing this from physics. So we need to know. We need to computate how much power we can get from the wind. Right? We've been talking about wind all the time, but give me some hard numbers. You could calculate the power from the wind to the turbine. The power of the wind is equal to 1/2 of the area that the blade sweeps, the whole area, multiplied by the air density of the wind, and then multiply by the velocity of the wind cubed. Okay, so the wind power makes a huge, the speed of the wind makes a huge deal because it's a cubic function. Okay, this is the total power you could get from the wind itself in your air, the area that the blade sweeps. Okay. Now, this is not what we could get out to the power grid because we still have the actual wind turbine itself, right? We can include the wind turbine efficiency and multiply that by kind of a percentage, C turbine. Okay. The efficiency turbine in general is somewhere between 25% to 45%. Okay, so if it's a 30, let's say it's 25%, you would take this number, multiply by 0.25, and then that's how much electrical power comes out to the power grid. Okay, we'll talk about why it's limited to this, but this is very typical. Okay, are we leaving a lot on the table? Yes, we are, because 25 to 45% is not exactly good, but this is a limit of our design that we have in today's world. If you could break this to like 80%, you'll be a billionaire in a year. Okay, but unless you can break the laws of physics, we're kind of stuck with that number. Okay. Now, let's do an example just to see the number crunching. Okay, determine the power output of the wind turbine with the data to the left, right? I should probably say right. Okay. Blade length is 5 meters. Wind speed is 5 meters per second. Air density is 1.2 kilograms per meters cubed. And this is very standard wind density at sea level or close to sea level. Power coefficient of the wind turbine is 0.3. Okay. So we can number crunch all this. I mean, first thing we need is calculate the area. Okay. Now, the blade sweeps in a circular area, so we got to think about what's the area of a circle. Area of a circle is always pi r squared. So the area is equal to 3.14 pi times 5 squared, because that's the blade length, which is equal to 78.5 meters squared. So that's the sweep area of the whole wind turbine. Okay. Now let's calculate the power. Power of the turbine is 1/2 times the area, which is 78.5 meters squared. We just got that here. Times the pressure of the air, which is 1.2 kilograms per meters cubed, times the velocity of the air, which is 5 cubed. So 5 meters per second cubed. And then the turbine coefficient is 0.3, so multiply by 0.3. You literally just number crunch as a calculator. I got 1.77 kW. Okay, and just to give you remember, 1.77 kW, that's might be enough to power your house. Maybe, maybe not, right? So we'll say this. So you live out on a farm, you can install this, and as long as the wind is constant at 5 meters per second, again, that's like what, 10 miles per hour, so you'll be able to power your house. Okay. So with that, I want you to do 2 exercises where we're going to modify that previous wind turbine design to see what has a bigger impact. Okay. So we want to modify wind turbine design by increasing the blade length by 6 meters. Previously it was 5, so let's just do some number crunching and make it 6. And how much power do we get? Okay. Let's change this around. Everything else stays the same. So answer in kilowatts. And then do a second one where we'll go back to 5 meters, but let's install it in a different location where we get a little 20% increase in wind speed. So instead of wind speed being 5 meters per second, it's 6 now. Okay. That way, I want to see what makes a bigger impact. Right? Does more wind speed make a bigger impact, or does having a bigger blade make a bigger impact? Okay. And then we'll do some compare contrast when we come back. Okay. So let's take our 10, 15 so minute break, and let's work on these 2 simple problems. We'll come back, check your answers, do some compare, and keep going on with the lecture. Okay. So see you in a little bit. All right, hello, welcome back to Triple 135, Chapter 7, Wind Power. So we're back from our 10 to 15 minute break, and let's check out these wind turbine design modifications. So first one, we increase the blade length to 6 meters. So let's just redo all your calculations. In green is what's changed. So we have r squared is 6 squared instead of 5 squared. So naturally, we're going to have a bigger area. So it's going to be 113.1 meters squared instead of like the 78. So just go ahead and plug that number right here. Everything else stays the same. Our power output is now 2.54 kW. So from 1.77, it already got like about 700 out. Okay. Let's go and do the wind turbine design, except now the wind speed has changed. So we're going, area is going back to normal, 78.5 meters squared. But now we're going to put in wind speed of 6 meters per second. So go ahead and number crunch that, and we get 3.05 kW. Right? So that's almost what, 1.3 kW more than our original design. Okay. Other than that, I mean, it's just a pretty standard plug and chug. As long as you know what these numbers mean, everything else is pretty simple. Okay. Now let's do some comparison. What are the results? The original wind turbine design was 1.77 kW. With the increase in turbine blade 20%, we got 2.54 kW. Or we increase the wind speed by 20%, we get 3.05 kW. Right? So which modifications to wind turbine design had the most impactful impact on overall power output, and why? Obviously, bigger number better, wind speed. right? And the reason why is because the wind speed, the power is increased. The power is increased by the wind speed at a cubic rate, meaning 6 cubed is better than 5 square or 6 square, right? So that's a big takeaway here. So it is critically important to find a site with the highest wind speed possible. That will exponentially get you more power than any other type of design modification. You could do all the fancy tools in the world, but nothing is going to be more impactful just than getting a faster wind speed to your wind turbine, right? So if you got a slow wind speed, nothing's going to fix that, right? Just go find a place with higher wind speed. Okay. So kind of here's two tables that show the difference if we change your wind speed from let's say the ideal one in the our wind turbine specs was 17 meters per second. Here they're showing what happens if it's locked at 10 meters per second, and then the length of the blade changes, so you can see it does increase, right? This table right here shows that if we have a constant blades length, but the speed of wind increases, that also has an increased factor, which the wind speed is going to have a bigger increase because it's cubic over the previous one here being square function. Okay. So it's just reinforcing the idea that wind speed is more important than any other part of your design. Okay. Now, let's talk about that 0.25 to 0.45 wind efficiency, the efficiency factor, right? Now, there's a famous physics law called Bett's law that states the maximum efficiency of converting wind power to mechanical power with a wind turbine design is 59.3%. You physically cannot get more than 59.3% efficiency out of wind, otherwise you're breaking laws of physics. Okay. So physically, what's the reason behind this? When you have the wind blades turning, some of the wind will always pass through the open area between the blades. The blades is not a solid disc, right? The blades are actually pretty thin, they go fast, but as there's a lot of gaps between the two blades. Because there's a lot of gaps between two blades, every wind that passes it, you just lost that energy, right? So theoretically, if we wanted this to be 100% the wind energy, what would happen? Well, the wind has to blow into the turbine and then dead stop afterwards. Literally means it's 0 meters per second, right? That's harnessing all the wind energy. And that's not physically possible with a wind turbine. Wind turbine will let some of the air through, okay? If you magically have a giant brick wall, I suppose, and all the wind hits it and the molecules hit it and stop and fall to the ground, then yes, then you have 100% wind energy efficiency. But then you're not making electricity, right? You're just stopping it with a brick wall. So it's just wind blow, every molecule that blows past the wind turbine blades, that's lost energy. And we can't help it, right? For the turbine to spin, we have to let some of the wind through. Okay. So that's just, we accept that factor. Okay. And even the best possible, just, saying, oh, let's cover like 30% of the area with the blade and 70% of the wind through, or whatever the mechanical engineers want to go, they could not break that 59.3%. They tried, and they said, this is the limit. So we got to live with it. Okay. What variable in the wind power, what variable in this wind power equation represents this law? So remember that turbine power we calculated? This 59.3% is baked into that turbine coefficient. So remember, this turbine coefficient has this maximum wind efficient conversion already baked into it, in addition to all other components of wind turbine. You have the mechanical bearings, the mechanical friction, you have the gearbox, you have the generator. Every device that power passes through, you always pay some efficiency tax, right? Nothing is 100% efficient. Everything is like 95, 98% efficient. But if you take a 98% efficient step and you have to go through 10 of them, you're going to start eking out some. The error is going to stop propagating, and you'll get down to that 30 to 40% efficiency. Okay. So even starting at, let's say, 59, we go through 5 devices, it can go down to 45 pretty easily. Okay. So we try to make it as efficient as possible, but we have to pay the piper sometimes. 25% to 45% is about the best we could realistically get from wind turbine design in today's world. Okay. So that's Beck's law, a very famous one that proves that you can't get all the wind. And I argue with environment like people on Reddit all day long about this stuff. They think, why can't we get all the power in the wind? Let's the wind could power the whole entire United States, start 5 times over. I'm like, no, you don't know what you're talking about. Learn some design first before you start spouting stuff off. Okay. So we know that wind speed is that's just nature. We just pick the right spot and then it blows. There are some things we can control. One thing we control is the length of the blade. Normally the blade is fixed. It's just a big tube of carbon fiber or fiberglass or steel, I guess, right? But the blade, we can actually put, if we can make mechanical devices to make the blade slide in and out to increase the actual length. And that will then increase the overall diameter, overall area of the blade itself. And we know by increasing the blade, will increase power as well. Okay. So variable area wind turbine blades is a thing. They're expensive, but people use them sometimes. Okay. So remember, once we decide on geographic area, we cannot change the wind speed. That's just nature doing its thing. But by clever engineering design, we can change the blade area on demand. This can change within seconds if you need to. Okay. When would we want to increase the blade length on demand? Well, let's say the wind slows down one day, right? So normally it's fast one day, but another day it slows down for some reason. We can increase the blade length to then make up for the lost power of the of the slow wind, right? So increasing the blade length will capture more wind power. So that's a good thing. So on slow days, increase the blades, we get constant power output, right? When would we want to decrease the blade length? When the wind is too fast. So let's say the wind is blowing too fast today. It's past the limit of where the design it likes. We could damage the wind turbine if it's too fast. By decreasing the blade, we're decreasing the area, we're lowering the power output, so we're not stressing the mechanical system as well, right? So when it's too fast, let's pull in those blades a little bit, lower the mechanical stress on the blades, make sure they don't snap, and then we just have a catastrophic failure. Okay. So variable wind turbine blades, that's the thing, sure. Okay. Now, we did some very, very light design of calculating power, trying to understand maybe a few little gimmicks of the wind turbine. Well, let's say you end up at a design firm. How can we accurately design a wind turbine blade and the whole wind turbine itself? Not just basic calculation, but go to full length of every single cross section, checking the wind flow, the gradients, all this very, very complicated stuff, right? You can't just make something and just hope and pray it works. We have a lot of design tools we can use. Okay. And once we make a design, we have to verify that from a mathematical modeling standpoint, it works. Okay. One way we could do that is called a finite element analysis for mechanical systems or blade design in this case. It's a computer-aided design that uses very complex mathematical algorithms to ensure very precise accuracy of the air flowing over the blade. There's fluids and flow mechanics involved, right? There's very, very complicated second, third order differential equations programmed to these kind of AutoCAD design softwares that uses finite element analysis. Okay. Another way we could do that is the physical testing. So let's say we make a design. We use a finite element analysis to verify it works on mathematical models, but I still want to verify that it works physically, right? Because that's the way I know. You can have all the mathematical calculation modeling you want, but I won't trust something unless I physically see it work. Okay. And that's what the physical testing does. So what we can do is we could get a wind turbine. We could put the shaft here. We could put a generator here, right, and attach it to a dynamometer, right? A dynamometer is just literally there to record the power output. Okay, so we take it out, we disassemble it, put it in a on a bench, and connect sensors to it, and we run a bench test. Okay, you took EEE 117, right? You built circuits with oscilloscope, plugging in, checking voltage. That's called a bench test because you're like putting on a bench. So we observe performance on a bench test and wind tunnels and verify that it's operating to the spec that we designed for. And if it's not, we got to go back and redesign it and keep going, maybe a few iterations until we get the acceptable results that we want. Okay. Now, once that's done, we typically go and have a prototype and we put it out in the market to maybe a few utilities that are brave enough to try our products, and we'll give it maybe a few years to verify that it works. And one way you could verify it is called a SCADA verification. Now, if you heard of SCADA before, it stands for Supervisory Control and Data Acquisition. It's basically a network of sensors that will have electrical outputs, and you all feed it to like a modem or a network device, and then that just records it on a microprocessor for a bunch of data collection. Okay. So ideally, you want to collect data of in-use wind turbines over the life cycle of the product, right? We want this. I want to have the SCADA set out there for 5 years, constantly monitoring the system. And if it's smart enough, it could sense irregularities and flag it and call us and say, "Hey, we're getting some issues here. The bearing's wearing out. There's too much vibration. There's electronic devices burning up." There's a bunch of things we could program it to do, and that gives us years and years of data, which we could then extrapolate trends and find these breakpoints, and then make a new improved version. This is where like version 1, version 2, version 3 comes out. Why do we have a version 2 or version 1? Because version 1 we let go for 10 years in the field. We figure out what failed first. So version 2 will fix those failures, right? And then we'll have an improved model, and we sell that. And we just keep going until we're happy that it's a solid product. Okay. So that's pretty much the life cycle of a design engineer. Is you're just making sure your system works and it's satisfactory to the customers. Okay. So in summary, talking about wind power systems, we just scraped the very top of it. Okay. Wind flows in various forms. The ones we care about is laminar flow, which is smooth airflow, and turbulent airflow, which is all scattered everywhere. We want laminar flow because that's the best for our wind turbines. Okay. Wind power can be calculated where the power output of the turbine to the electrical system is equal to 1/2 times the area that the blade sweeps times the air density of the locally around you, multiplied by the wind speed cubed, and then multiplied by the turbine coefficient of somewhere between 0.25 to 0.45. Okay. Wind turbine output power will vary based on the wind speed the most. So the wind speed has the highest factor of power variation. Then it'll be blade length because that affects the area. And then other things like after that is the air pressure and other small things. But those don't really change. The two things we have the most control over is the location where the wind speed is, and then the blade length, which we design. Okay. Bette's law is very important because that states that the maximum efficiency to harness wind power is at best 59.3%. So you're always going to leave 40% of that power just to nature. You can't take it all. Okay. We can always verify wind turbine designs by using the finite element method to design it, finite element algorithms to design or verify our designs. We then do physical lab testing and bench testing and wind tunnel testing to make sure it works. And then we can have years of SCADA data collection to verify the longevity of our product and fix any ongoing issues for the next version that comes out. Okay. So that's all I have for today. Kind of scraping the top of wind power systems. We'll come back next week and start talking about wind turbine blades and more complicated designs. Okay. So thanks for showing up. Hope you guys have a good rest of the week and see you next time.